This video explains design of beam, an 800 mm by 400 mm rectangular reinforced concrete beam which has a span length of 8000 mm, simply supported. The beam is required to support the following uniformly distributed service loads. It has a permanent dead load of WG 20 kN per meter. It includes the self weight, and imposed live load WQ is 24 kN per meter. Now the question is to find assume the beam is singly reinforced, determining the required longitudinal reinforcement at the midspan by first principles, so that is the matter of first principle, or by solving the quadratic equations. B question is locate where along the span one half of the longitudinal reinforcement can theoretically be terminated, and the critical load combination for the strength is ED 1.2 G plus 1.5 Q, and the characteristic of concrete is given 32 megapascal, and there's to be 40 millimeter cover to the R10 stirrups. So all the details that we're going to have, that will be put it into the figures. Now first of all, dead load is given WG 20 kilonewton per meters. So there is a 22 kilonewton per meter dead load is given in the questions. Live load is given WQ equal to 24 kilonewton per meters. So that live load is given 24 kilonewton per meters. The calculation for the total design load is W star is ED 1.2 G plus 1.5 Q. So that is 1.2 times 22 plus 1.5 times 24. Let's give us 62.4 kilonewton per meter. So this equation also given in 1170.0 2002. Now we need to assume, because we need to calculate what is the tensile reinforcement here at the bottom. We don't know what are the area of tensile reinforcement, so we assume that is diameter 24 N bars reinforcement. Now first of all, we need to calculate this small d. What is small d? Small d is nothing but the overall depth minus the cover minus the stirrup diameters minus the half. So it's just measuring from the top of the beam to the center of these reinforcing bars. So small d is 800 minus this cover 40 millimeters, that is given here in the questions. Cover is 40 millimeters minus the stirrups that are used to hold the reinforcement. That stirrup is also given R10 10 millimeter stirrups, so that is take away stirrups, minus we assume that is 24 millimeter dia, so we just need to half by 24, so that is measuring from center of this reinforcement to the top, that give us 738. So this depth is 738 millimeters. Now for simply supported beam, is given in the questions, is a simply supported beam. We can draw the diagrams, and it has a loading of 62.4 kilonewton meters. That is, let's say W star 62.4 kilonewton per meter. And if I draw the bending moment diagrams, it has this parabola, and the length of this one is 8 meters. So if I like to calculate the moment, design moment here, M star is WL square over 8. It's not just a structural analysis. 62.4 that we substitute times 8 square over 8, that's give us 500 kilonewton meter. Once we calculate the design moment 500 kilonewton meters, we can go ahead and draw the stress distributions and the linear strain stress distribution force and the moment. So this is the cross section 400 millimeter by 800 millimeter. We already calculated 738, that is small d. We calculated 738 millimeter small d. That I placed here. Please note this is measuring from center of this N24 bars to the top edge of the beam. Now if I measure this strain value is a concrete compression, maximum concrete compression strain is 0.003, and then that is given in the Australian standard. So if you look at here on the page number 110, we can show it to you here on the clause 8.1.3. it says the maximum strain in the extreme compression fiber is taken is 0.03. so it's on clause 8.1.3. And then this is the strain in the tension strain in the steels. Now we discussed the stress distributions of the concrete. Now the stress distribution is maximum stress distribution is alpha to FC dash, and the depth of this stress distribution is gamma dn. And these are the tensile stress in the steel, and these are the compression stress in the concrete. Please note, this is the neutral axis. Concrete below the neutral axis is subjected to tension force, so there is no any forces in this region. There are compression forces, not taking whole portion but just taking the average of these effective stresses here. Now if I take the whole this distribution as a one force, that is the compression force in the concrete, that should have a applied in the center of this length, which is half of lambda dn. And similarly we can have tensile force in the steel bars, which is applied here. Distance between these two, compression force and tensile force, is represented by Z, which is a lever arm, and this is a moment. So I can write force and moment, which can be calculated MUO, that could be T times Z, or MUO is C times Z. So we can use any of these equations. Now let's start talking about finding the concrete forces. Now concrete force is equal to stress time area. So the C is the concrete force is equal to stress is alpha to FC dash times the area is lambda dn times the width of this concrete. We discussed this in the previous video. Now we need to calculate alpha 2. Alpha 2 is 0.85 minus 0.015 FC dash, that is should be greater than 0.67. that is given in clause 8.1.3 on page number 110. That is here, and clause 8.1.3 it has given alpha 2 value is 0.85 minus 0.015 FC dash, and that is 0.16. that is given here. Now in this case alpha 2 should be greater than or equal to 0.67. substitute the FC dash value characteristic, which is 32 megapascals, and that 32 megapascals given in the questions characteristic strength. That simplification gives 0.802, which is greater than 0.67, so we can take 0.8. if it is less than 0.66, we need to take 0.67. Gamma value equations given again on the same page 110 on the Australian standard. If you go to 110, you can see the gamma equation is 0.97 minus 0.025 FC dash. So that is the gamma value, and we take this gamma is equal to 0.89. if you simplify this, it gives you 0.89. again it is to check whether it's greater than 0.67 or not. If it is greater, you just take it gamma 0.89. so in that case we take concrete is equal to alpha 2 FC dash times gamma dn times P, so that is 0.802 times 32, that is given in the questions. Characteristic strength of the concrete at FC dash 32 megapascals times gamma, we just calculate as 0.89. dn we don't know, dn is nothing but the depth of the neutral axis. So if I put it dn here, this is just a dn, depth of the neutral axis, so that we don't know. That dn times width of the beam is 400 millimeters. That is given again in the questions. If you look at the start of the question is 400 millimeters. So that simplification give 9136.4 dn, and we just give them equation 1. Next video explain the next step of the solving this example. Thank you.